Welcome. Good evening. My name is Dikpo Tekpede. Today I'll be presenting on the Central Limit Theorem. And what I'll be trying to do is, first and foremost, I'll run through the theorem so that we can get an idea about the Central Limit Theorem and what it's for. First of all, let's look at the Central Limit Theorem. What is it about, and why do we need the Central Limit Theorem? The Central Limit Theorem. The Central Limit Theorem was developed in order to combat sample error. There is no way in which sample is taken from a population and making judgment on the sample to infer on the population that there won't be an error. And in order to combat this error, the Central Limit Theorem was developed. The Central Limit Theorem is a group of four theorems or four theories. The first theorem states that it does not matter the population distribution that the sample is taken from. So what the first theorem states is that it does not matter the population distribution. It does not matter the population distribution that the sample is generated or taken from, as long as the sample size that was taken, as long as the sample size is greater or equal to 30, the sample's distributions of the mean, the sample distribution of the mean will be approximately normal. So the first theorem states that it does not matter the population distribution that the sample is taken from. So if you are going to take a sample and you want to take a sample from a population, every population will have a distribution, no matter the distribution of the population. But this first theorem is saying that, look, it doesn't matter what the population distribution is. The population distribution could be binomial, could be Poisson. It doesn't matter what the population distribution is. As long as the sample size that you are taking from that population is greater or equal to 30, the sample distributions of the mean will be approximately normal. So what will be normal is the sample distributions of the mean. And I've already explained the sample distributions of the mean earlier. So we're saying that it doesn't matter what the population distribution is. As long as the sample size that you are taking from that population is greater or equal to 30, the sample distributions of the mean will then be approximately normal. So that's the condition for the sample distributions of the mean to be approximately normal. Now let's look at the theorem 2. Theorem 2 states that when the population distribution is normally distributed, when the population distribution is normally distributed, the sample distributions of the mean, the sample distribution of the mean will also be normally distributed. Will also be normally distributed. regardless of the sample size. Regardless of the sample size. So, what this number 2 theorem is saying is that if you take a sample from a population that is known or that has been agreed or that has been certified to be normally distributed, that sample distributions of the mean will be normally distributed regardless of the sample size that you take. So it doesn't matter the sample size, whether it is 3, 2, or 150, or 300, as long as the parent, the population, or the parent distribution in which you are taking that sample from is normally distributed, the sample distributions of the mean will also be normally distributed. That's the second theorem. Now, the third theorem. The third theorem states that the mean of the sample distributions of the mean, the mean of the sample distribution of the mean, okay, which is regarded as mean of the sample distributions of the mean, which is saying the mean of the mean, okay? So the mean of the sample distributions of the mean is equal to the mean of the population. So we're saying here that the mean of the sample distributions of the mean is equal to the mean of the population. That means if you have a mean of a population and you want to know the mean of the sample distributions of the mean, we are saying they will be equal. And I looked at, if this is a population, I took this node and I said if this is a population and I divide this population into 4 subsets, that means making this population have 4 different samples. So if this population has 4 different samples that I've taken from it and I exhaust these 4 different samples, which makes it sample distributions of the mean, and I now find the mean of each of the sample. Now, the mean of each of the sample, that means the average of the mean of each of the sample, that's the arithmetic average of each of the mean of the sample, will be here. Because if I find the mean of this, mean of this, mean of this, mean of this, it will be at this center. And the average of the mean of the sample is here. If you take the mean of the whole of this population, the mean of the whole of this population will also be here. So you can see it's equal. The mean of the sample distributions of the mean is equal. That means the mean of the sample distributions of the mean is equal to the mean of the population. That's what we are saying. So that is the third theorem. Now let's go to the fourth theorem. The fourth theorem states that the standard deviation, okay, which is equivalent to the average deviation, okay, the average deviation. Okay, so we're saying the standard deviation of the sample distributions of the mean. The standard deviation of the sample distribution of the mean is equal to the standard deviation of the population divided by the square root of the sample size that you picked. So what we are saying is that if you want to find the standard deviation of the sample distributions of the mean, it's equal to the standard deviation of the population divided by the square root of the sample size. So that's what the fourth. So we have here four theorems, which makes up the central limit theorem. And that's the fourth theorem we're going to be applying. Because this theorem, we'll be using it throughout this course, because we'll be dealing with samples. We don't deal with population in real life. Everything we'll be doing with samples, when we are collecting data from our processes, whatever the type of data is, if it's a survey, if it's a quantitative data, no matter the data we are collecting, it will always be samples. And if in order to solve this particular sample, whichever means we want to test or solve it, we are going to definitely use the central limit theorem. So knowing the central limit theorem at the back of your hand is very important. But what we're going to do, we're going to apply this particular central limit theorem to a case study. So let's look at this case study here. The Gajagas case study. Okay, if you look at the Gajagas case study, if we look at it here, now let's look at the Gajagas case study. Gajaga is an electronic company that manufactures circuit board. So that is clear that Gajaga is an electronic company that manufactures circuit board. Now, that is clear. If that's what they do, that's what they've been doing. When they've been doing it, we don't know, but they've been doing it. And the average imperfection is like saying the average defect on a board has a mean of 5, which means it has a population mean of 5, with a standard deviation of 2.34, with a population standard deviation, which is represented by this symbol called sigma, of 2.34, when the production process is under statistical control. So what we're saying here is that there has a mean of 5 and a population standard deviation of 2.34. Now, that stops it, full stop. A random sample of 36 circuit board has been taken. So here, a random sample was taken from this population of production of circuit boards. A random sample of 36 circuit boards was taken for inspection, and a mean of 6 per board was found. So this mean of 6 is part and parcel of this 36. This 36 sample size, or sample size of one sample that was taken, is 6. So the question is now, what is the probability of getting a value less than or equal to 6 if the process is under control? So this question is saying, okay, we discovered that there is a population distribution here. The population distribution, as we know it, is a Poisson distribution. Why? Because it says that the average imperfection in a board is 5. So this is a Poisson distribution with a known average. It's a Poisson distribution with a known average. That's the population average of 5. And a population standard deviation, of 2.34. So this in itself is a Poisson distribution, because first of all, a Poisson distribution is number of events that occur within an interval or a continuum when the average of such events is known. Here, the average of imperfection here is known, which is 5. And so this is a Poisson distribution. Ordinarily, if you want to find what is the probability of getting a value of 6, ordinarily, if you want to find this, we'll use the normal Poisson distribution. That is P, let's make it like this. P less than or equal to 6 is equal to mean raised to power x, which is 6, exponential minus the mean raised to power 6 factorial. Now, the problem with this particular equation is this less than or equal to 6. We can't use this because this is supposed to be used for a discrete distribution. This Poisson distribution is a discrete distribution. It's a discrete distribution. It's a discrete population distribution. And hence, we cannot find the probability of less than or equal to 6. If we are looking for the probability of 6, yes, we can have it. We can use this to solve the probability of 6. Okay, if you want to just look for probability of finding 6, we can use this. But that's not what the question says. The question is looking for the probability of 6 or less than 6. So what we are looking for is the probability of lower than 6 or equal to 6. Here we cannot use this discrete population. So we have learnt the central limit theorem. And the central limit theorem, theorem 1 states, if we look at theorem 1 and what it states, very simply, theorem 1, if we go back to our theorem 1, it states that theorem 1 states that it does not matter the population distribution as long as the sample size we take is greater than 30, then the sample distributions of the mean will be approximately normal. So here, what will be approximately normal is the sample distributions of the mean. So we know that because our sample size here is 36, n here is equal to 36, and 36 is greater than or equal to 30. So our sample distributions of the mean will be approximately normal. Now that we know that our sample distributions of the mean will be approximately normal based on theorem 1, the next thing we need to find in order to find what's the probability of getting x less than 6. So first of all, we don't even know what the mean is, the mean of the sample distributions of the mean. If we want to know what the mean of the sample distributions of the mean is, we already know that from theorem number 3. Theorem number 3 states that the mean of the sample distributions of the mean is equal to the mean of the population. And what's the mean of the population here? Here, the mean of the population, despite the fact that it's a Poisson distribution, is 5. So the mean of the population is equal to the mean of the sample distributions of the mean. So that means the mean of these sample distributions of the mean is 5. And what's the question? The question is asking us, let us find the probability that the value is less than or equals to 6. So 6 will be here, if that is 5, and this is what we are looking for. We are looking for this proportion. Another thing we need to take note of, which is very important, is the fact that we need the standard deviation in order to standardize this normal. And since we have found the mean of the sample distribution of the mean, the standard deviation of the sample distribution of the mean could also be found in the 4th theorem, which says the mean of the standard deviation of the mean is equal to the mean of the population divided by the square root of the sample size. So here, we know, if we don't know the standard deviation of the sample distributions of the mean, but we have the standard deviation of the population, and we also have the sample size of this population. So in order to find this, we can easily find this by just calculating 2.34, which is this population standard deviation, square root of 50. So that's it. Okay? So by the time we do that, this will give us our standard deviation of the samples distributions of the mean. So now that we have that, we can easily solve that. How do we solve that? you can easily solve that. So that will give us 0.39, I think. This will give us 0.39 after calculation. So we have 0.39 here as our standard deviation of the sample distributions of the image. So we can standardize now. To standardize this, what happens is the mean will be 0. And now I want to find what the z is. And we know that z is equals to 6 minus 5 all over 0.39. So by the time we are through, our z will give us 2.56. So here, 2.56 will be here. So we will take 2.56 here, and we'll find the proportion that is here. Okay, so the next thing to do is to go to the Z table. Okay, so that's the next thing we'll do, is to go to the Z table. On going to the Z table, we can look for 2.56 on the Z table, and 2.5, 0, 1, 2, 3, 4, 5, 6 will give us 0.948. So we have 0.9948. So we have 0.9948 here. 0.9948, which is same thing as approximately will give us same thing as 0.995 to 3 decimal places. And that's it. Okay? And this is how we're able to get the proportion, the probability. So the probability that we are going to get 6 and less than 6 is 99.5%. So from here, we know that to get 6 or less than 6 is going to give us 99.5%. And we can use Minitab to arrive at the same thing. We can use Minitab to arrive at similar thing that we just solved now. To use Minitab, we just put all the data there. We go to Start, Basic Stats, and we go to one sample Z. Because what we picked was just a sample. We changed it to summarize data. And we know from here that our sample size is, our sample size is 36. Sorry, I think I made a mistake in another place. It's 36, but I think we still got the same answer. Then the mean was 6. Okay, sorry. The standard deviation was 2.34, if I remember. Then the mean, the hypothesized mean, okay, was 5. And we click on option to look at less than the hypothesized mean, because we are going lower. Okay, click OK, and we'll click OK, and we see that the P here, the P value, the Z value was 2.56 that we picked, and the P is 0.995, which is the same 99.5 that we got here. Okay, so I hope that was able to explain the central limit theorem.